Good afternoon. We would like to introduce our project that is titled What if Neural Networks Had SVD? This article studies already research approach and it aims actually to facilitate it. Consider storing dense layers in neural network in the form of its SVD decomposition. What it can be used for. We had an example in our first homework when it allowed us to decrease the number of parameters without the loss of accuracy. Also, it can be useful to facilitate matrix operations like inversion. The idea is to perform gradient descent on SVD matrices, but there is the problem, how to preserve orthogonality of matrices U and V while making a gradient descent step. A popular approach here is to decompose orthogonal matrices in a product of householder matrices and perform gradient descent on corresponding householder vectors instead. And this paper suggests facilitating the existing methods for computing matrix-matrix multiplication of householder matrices on some arbitrary matrix of corresponding dimensionality. They propose algorithm that has time complexity big O d square m, where d is the number of householder matrices and their dimensionality. The previous approach had time complexity big O d cube. So to construct such algorithm, they consider the following lemma. It states that for any set of householder matrices, there exist such matrices W and Y, that for the product of these householder matrices, that holds an equality similar to the definition of householder matrices. In the algorithm, there are two steps. The first is to divide the initial set of householder matrices in D divided by M parts and compute corresponding matrices Y and W in parallel. And then we compute the product of the obtained subproducts sequentially. There are D divided by M matrices in sequential multiplication. So it results to the total big O dm squared time complexity, or d squared m time complexity. They also propose a backward pass of this algorithm is that is computing partial derivatives of the last function, and it has the same time complexity, but I want to go deep into the details, and we will head to the experiments.
In the first experiment, we consider the square weight matrix V. And we also consider different functions phi that reparametrizes our matrix V in such a way that phi of V is orthogonal and we can perform gradient descent with respect to V. And we consider several ways to construct function phi. The first one is householder decomposition, which can be implemented in the fast way by using first stage method, and speed up is because of parallelization, or it can be done sequentially. Also, we consider matrix exponential function and Kelly map approach. Our goal is to compare the running time of a gradient descent step. It means that we compute the forward pass, phi of V multiplied by X, and then we compute the gradients with respect to V. And we compare fast stage with the alternative algorithms. And here is our result. As it was expected, sequential method is the worst. Then we have exponential curve, Cayley curve, and the best one is the first stage method. We can see that speed up of more than 11 times if we compare with sequential algorithms, and speed up about 5 times if we compare with exponential, and fast stage outperform Cayley methods in more than 2 times.
After that, we considered one of the numerous applications of fast-stage matrix multiplication that can be found in recurrent neural networks. In 2018, spectral RNN architecture was proposed. It deals with the problem of exploiting gradient by the means of parametrizing the transitional matrix with SVD decomposition and controlling corresponding singular values. It was proposed to constrain singular values by applying sigmoid with some additional centering and scaling to the parameters updated with gradient descent. It's easy to see that the derivative of the last function with respect to the parameters of the recurrent network is strictly connected to the spectral norm of the transition matrix, and the power of the transition matrix in this relation equals to the number of recurrent applications of RNN. It was observed by them that this approach also tackles the problem of vanishing gradient. So in our experiments, we aim to compare the time consumption of vanilla sequential SVD parametrization in recurrent neural network and its facilitation with fast dash. We considered spectral recurrent neural RNN that gives 93 accuracy on MNIST and expected acceleration for the choice of m that is equal to square root of d, where d is a hidden dimension of RNN. So expected acceleration was from big OD to big OD divided by square root of d. So we can see that the slope actually, the slope of this graphics actually differs in this ratio. So the experiment gave expected results.
And the summary, we have studied an efficient matrix multiplication parameterization that can be implemented effectively on GPUs. And target that we achieved, we compare time consumption of algorithm fast stage and other algorithm, and we compare forward pass and backward pass. And also we studied running time of RNN with SVD parameterization of transition matrix, fast and sequential approaches. Also, fast stage can be implemented for accelerating such matrix operations like inverse or determinant, and also we can do more experiments with RNN. Thank you for your attention.